Hey there, so I'm very excited about today's video, like usual, because we're moving into section 3.4 where we look at the definition of the derivative. So let's get started. Okay, section 3.4, the definition of the derivative. So we want to first talk about the tangent line. So in the previous section, we saw how the formula, the limit as h approaches 0 of f of a plus h minus f of a over h was used to calculate the instantaneous rate of change of a function f at the point x equals a. And remember that this was just the average rate of change, and we let the difference between the two x values approach 0, and that's what this h letter represents. Okay, so now we're going to explore a geometric interpretation of this limit. Okay, so let's take a moment and just think about back in your geometry days. Okay, in geometry, a tangent line to a circle is defined as a line that touches the circle at only one point. Okay, so in this image right here, I've got like this top half of a circle, and we can imagine that this is a tangent line, and it just touches the circle at this one point. Okay, if the tangent line passes through the circle and touches it at more than one point, then it's called a secant line. And we're going to get into the differences in that in just a minute. Okay, the tangent line to any curve, not just a circle, at a point P on the curve should touch the curve at P, but not any points nearby, and it should indicate the direction of the curve. But a curve is a little bit different than a circle because it has all these different ways that it can bend and move around, and so we're going to have to be a little bit more careful. Okay, so since we want the tangent line to indicate the direction, which we're going to think of as the slope of the graph, where it touches it, we must define the idea of a tangent line to the graph of a function more carefully. So on the right-hand side, I just have this generic curving function here. And so with a few different tangent lines, and so this one on the left side here, that looks pretty good. It looks like maybe you could imagine that that's the direction, the slope of the graph right there, and it touches it at only one point. But a little bit later, that we've got a different tangent line right here, and the line actually intersects the graph and goes through it, which would not happen for a tangent line on a circle. And then this other tangent line over here at the bottom of this little dip right here, that looks pretty good, but this line comes over and it intersects the graph in a different location. So we're going to have to be a little bit more specific about what we mean by a tangent line to any curve. Okay, so in order to develop a definition for the tangent line, we're going to want to first talk about a secant line. So let R be a fixed point with coordinates a, comma, f of a. So some x value a, comma, plug that value into your function to get the y value. Okay, so any a value. On the graph of a function y equals f of x. Then we're going to choose a different point s on the graph and then draw the line through R and S. Okay, so then this line that goes through R and S is going to be called a secant line, where it's two separate points on the graph and you can draw a line through it. Okay, and then what we want to do is we want to make sure that that S has coordinates that are related to the first point R by just adding H to the X value. So we're going to say that S has coordinates A plus H, comma, F of A plus H. Okay, so starting with some A value, just go H off to the side, okay, some distance H. Then the slope of the secant line is going to be given by, and then it's literally just the change in y divided by the change in x, which is, hey, guess what? It's that average rate of change formula that we've worked with in the past. And since we can work this out, this is y2 minus y1 over x2 minus x1. And then very nicely, the a's will cancel in the bottom, and we get this difference quotient that we've talked about in the past, this f of a plus h minus f of a over h. Okay, so that will be the slope of the secant line. Okay, and then yeah, notice that this slope corresponds to the average rate of change of f from x equals a to x equals a plus h. Okay, so looking familiar, that's why we did the work in the previous sections to pretty much build towards this topic. Okay, so then the tangent line of the graph y equals f of x at a single point, okay, so not two separate points, at a single point a comma f of a, is the line through this point having slope as the limit as h goes to 0 of that slope of the secant line. Okay, and so that's that instantaneous rate of change that we studied in the previous section. Okay, now provided this limit exists. If this limit does not exist, then there is no tangent line at the point, and we'll talk about those cases a little bit later. And so I'll click on this link in just a minute, and this is very, very valuable to use Desmos here. As you know, I like Desmos a lot, so I'll click on that in just a second, and I invite you to be able to click on that as well. But what I want to quickly mention here is that the definition of the slope of the tangent line is identical to that of the instantaneous rate of change, okay? And the slope of the tangent line at a point is also called the slope of the curve at the point, and it corresponds to the instantaneous rate of change of y with respect to x at the point. And so back in the day, slope of the curve didn't make sense. But in calculus, now we can talk about the slope of a curve. Historically, we talk about the slope of a line. A curve has a different slope all over the place. And now this is where the calculus comes in, where we can actually find out what the slope is of a curve at any point. So very important as a visual aid, I want to click on this link here. And we'll go to Desmos real quick. And so let's play around with this. And I really want to emphasize the difference between a secant line and a tangent line, and how the tangent line ends up becoming the slope of the tangent line is that instantaneous rate of change at a single point. Okay, so here we go. I just have a function defined here. F of x is 1/4 x squared. So just a nice parabola here. And then we'll create a point r on the function. So like I said in the notes, it's going to be some value of x is a, comma f of a. Okay, and so I've got r right here. And then with Desmos, it's awesome. I've got a little slider going here where I've got a set as 1. But I could choose a to be, I could slide it around and pick different values. And then this other point on the graph S, that's going to be a plus h, okay? And with the sliders in Desmos, I can set h to be whatever I want, and right now I have it set at 3. So these are just two separate points, r and s, on the graph. And if I slide a around, as you can see, they'll move around a little bit, and I've just got two separate points on the graph right here. And of course, I can also move h around and make that point s get like farther away or closer away. So I've got some freedom to play around with these things. Okay, so that's where I can just define a couple of points to be on the graph. Okay, then what we're doing is we want to calculate the slope of the line through r and s. And remember that a line that goes through two separate points, we call that the secant line. So I've got that worked out. M is, and then this is just that definition of the average rate of change, f of a plus h minus f of a over h. And so this calculates the slope. We can see that right now the slope looks like it's 1.25. Okay, and then graph the secant line through r and s. And so this is a little bit fancy, but this is really just a secant line of the point slope form. And so if I click over here, I can turn on that line and we can see that there it is. That is the secant line. And if I move a around, we can see that depending on where r and s are plotted on the graph, that secant line goes through them, and we can see that that secant line is changing quite a bit, right? The slope changes, its position changes, all kinds of stuff changes. And then as we move h around as well, we can get that the secant line is changing as well. Now, by the definition, if I go back to the notes here, by the definition, the tangent line is that slope of the secant line as we let h go to 0. And so let's go back to Desmos here, and then this is the beautiful thing about Desmos, and you know how much I like Desmos already. If we let h go to 0, that is going to be a tangent line. So right now with h set at these numbers out here, r and s are some distance apart from each other. But if we let h go to 0, the limit as h goes to 0, we can see that this secant line gets these 2 points closer and closer and closer and closer until they land right on top of each other. Now h is 0. Notice that Desmos can't handle this anymore. The line disappeared right there, where r and s are now the same. And look, if I do the slope right here, Desmos says that it's undefined. And yeah, because if I'm putting h as 0, then we're dividing by 0, it's undefined. But as we noticed when we were working out the average rate of change, switching over to instantaneous rate of change, we did some factoring and canceling and some nice stuff to get that h to cancel. And so it's not actually going to be undefined when we do all of our algebra. And so I've got this notation here, and don't worry about this. We're going to talk about this notation in just a minute, but this is actually a way to tell us what the slope of the tangent line is. And if I turn on the graph of the tangent line, and again, don't worry too much about this. We're going to talk about this pretty soon, but I'll turn on that graph of the tangent line. This is the calculus. It's the loophole for that divide by 0 situation for the instantaneous rate of change. And now when the secant line has those 2 points are right on top of each other, that is now called the tangent line. And if I move A around, you can see that for the tangent line, it's always touching the graph at just that one single point where R and S are the same point. And you can notice that wherever it ends up on the graph, it seems like it's also indicating the direction of the graph. So that slope of that tangent line is actually going to be the slope of the function at that single point as well. Okay, so awesome stuff. I invite you to play around with this. Click on that link. Don't worry about messing it up too much because every time you click on the link, it'll reset. Okay, but yeah, play around with that. And I think it's just a really, really good visual aid to see how if we let H be any distance apart, we've got those two different points and you can get a secant line. But as soon as you let those 2 points go closer and closer, the limit as H goes to 0, then we get the slope of the tangent line. And so anyways, pretty cool stuff. Let's get back to the notes, but I invite you to play around with that a little bit. Okay, I'll make a separate video to pick up on example 1. It's that same function that's over there on Desmos. So we'll work it out algebraically, and then we'll also take a look on Desmos to make sure that it's still making sense with algebra, and we won't have to use Desmos to find these out. We'll do all of this algebraically, but we'll look back and forth just so that we can see what's going on and see all of the connections between the secant line and the tangent line. All right, so I'll make a separate video to pick up on that, so stick around.